Paper 2 GCSE Physicists. We know if you're doing higher tier, there is a multi-step equation coming. I'm going to have a look at some of the hardest ones today. So how can we spot them? They're always 5 or 6 marks without any units or conversions. There's loads of values given. They can seem really, really difficult to solve at first. I'm going to show you how to do them today. So please keep in mind, how do you kind of make sure you can solve them to the best of your ability? Keep calm. I know it's easy to say, but keep it cool. You can do it. And write down any equation you might need, ideally small on the side to make sure you don't waste all your room. Any equations at all that may help, and you want to make sure you work out something successfully. It's better to get 2 or 3 marks out of 6 than none at all for messing up, and in light of that, use the extra space, use the space on the back if you find that helpful to get your marks.
Question we've got here is a scary looking one. We know it's a multi-step equation, i.e. you need more than one equation because it's 5 marks and there's a load of information given to us. So let's have a look at what we've got. So let me underline the key things we've got. We've got a length of wire. Now I haven't given you the context of this question, just the numbers, but we've got a length of wire here. We've got some current. We've got a reading on a balance. Now it doesn't say what it is, but it's in kilograms. So we should be able to figure out that means it's mass. We've got a gravitational field strength, which on Earth is 9.8, and we are asked to work out the magnetic flux density of the magnet. So I've written the symbols in here. Let's have a look at the equation sheet, see what we can find them to help us. So one of the first things to notice is that if we're trying to find magnetic flux density, there's only one equation in the whole equation sheet that has magnetic flux density in it, and it's this equation here, which states that force equals flux density times current times length. The next clue we've got to figure out what else we need is that there is gravitational field strength. So there's only 2 equations that could be out of those that involve that. One is energy, potential energy equals mgh. The other one is weight equals m times g. Now this is a paper 2 one, so that sounds more likely. Plus we also know we've got mass as well, so that could be helpful in this question. Now, this question is particularly difficult because even though we've got our 2 equations, it seems like there's not got enough in common. They both have 3 totally separate, well, this one has 4, this one has 3 totally separate values. So what we're going to have to do is to do a little bit of physics detective work as well. And our physics detective work is that W stands for weight, and weight is a force. Now, if it's a force, then we can put it into this equation because we know F stands for force here. So that then helps us to figure out our first thing. And even if we couldn't figure that out, well, I know I've got mass, I know I've got G, so why not work out the weight? You know you could work out something from 2 unknowns, so let's just work it out and see what we get. So first of all, the mass, it's all given to us in the correct units. We just need to be able to put it into our calculator in standard form. So the mass is 1.2 times 10 to the power minus 3 times by G, which is 9.81. And that gives us then a weight of what does that come to? 0.01176 newtons, which sounds a bit low. It's a horrible decimal, but don't worry. The context of this question is quite a small force that we'd be expecting here anyway. Now, that's our first couple of marks all sorted. Next thing we've got to figure out is that as well as that being a force, being weight, we can also assume it's a force. All right. So now we know that, and I'm going to go down and use the lower bit just because I've done it big for the camera, but I've not got loads of room left. Now we know what that is. We've got the length in the question, we've got the current in the question, and now we've got the force. So the last thing to work out is our flux density. So let's use a little bit of FIFA for this one to make sure we're rearranging correctly. So FIFA means we've got formula, insert values, fine tune, and give an answer down below, just to make sure we're rearranging our equation correctly, because it's easy to mess this one up. So first stage formula, F equals B times I times L, write out again just in case you get confused. The force we now know, so I'm going to write that underneath it, 0.1176. Flux density, I don't know, so I can leave it as a B. I can also leave it as an X or a question mark if I want to. Either of those things are absolutely fine. Current is 0.8, length is 4.8 times 10 to the minus 2. Okay, now you could work out those 2 values multiplied together if you wanted to. That's absolutely fine to do. But either way, you should be able to figure out to get these values onto the other side of the equation. We're going to need to divide by them. Okay, so our flux density to do our fine tuning stage is going to be equal to, on this side we're going to have 0.01176 divided by both those 2 values. So I'm going to leave them in brackets here, but you could just work those out separately if you wanted to. And the last thing is just keep an eye on your brackets, put it onto your calculator. What do we get? Our answer, magnetic flux density, happens to be 0.306. There's no significant figures or anything like that, so you can pop that straight on the answer line, and that is our 5 marks. let's move over to our next question, and this one's all about motion and forces. So let's unpack what we've got. We've got a speed here, we've got a time taken here, and we've got another speed here, which is interesting. I'm going to come back to that in a second. And we've got a force, and the question asks us to work out the mass of an airplane. Now, it should be obvious just because of the number of values they've given us. They've given us 4 values and asked us to find a fifth, and it's 5 marks. This is a multi-step equation. Now, our tricky thing is here, because it looks like we've got 2 speeds. Okay, now again, with the context of the question, it might be a little bit easier. However, if we've got 2 speeds or 2 velocities, we need to be able to distinguish between which one's first, or the initial velocity, and which one's the final one. Okay, so it tells about an airplane landing at a speed of 80 meters per second, then it decelerates to a speed of 10 meters per second. So the symbol we're going to use is initial velocity, which is u up here, and final velocity, which is v, and that will help us find equations later that might help. Okay, now I'm going to write down on the side all different equations we could use, because there's actually a few we could use for this one. So just ones that, these aren't all correct, but just ones that have the values we need in. I could have force equals mv over t, I could have F equals ma, I could have this really long confusing looking one, the v squared equals u squared minus 2a, v squared minus u squared equals 2as, I could have acceleration equals v minus u over t, or change in velocity over time. Okay, obviously not going to use all of those, but it's kind of helpful, this alternative version of that, but it's kind of helpful to be able to look at and figure out what we need. Okay, now let's look at these in turn. So in terms of finding the mass here, I can't use this one because it's actually got 2 different velocities here, and I wouldn't know which one to put in there. Okay, however, I'm hoping it's kind of obvious. If I've got force, I've got here, now force is definitely in the question, so that's fine. If I'm trying to find mass, this one here, I need to find acceleration. Now, 3 ways of finding acceleration here. So let's see which one of these works before we then can use this in an equation here. Now, I'm going to end up using, these are basically the 2 versions of the same question to be able to find acceleration. Because do I have an initial speed and a final speed? Yeah, so that means a change in speed. Do I have a time? Yes, so I can use this one and then figure out the acceleration. Okay, so let's do one at a time then. So I'm going to do acceleration equals change in velocity, or a final minus initial velocity, divide by time, and we'll see where it goes with that. Now, we don't need to do any sort of rearranging here. We can just plug our values straight in. Starts on 80, gets to 10, does that in 28 seconds. So therefore, you've got 70 divided by 28. And now if we plug that into your calculator, we should find that can equal 2.5 meters per second squared, which is a nice kind of couple of marks, just regardless. So again, don't forget, even if you can't get the final answer, work something out, it will help you. Next then, we've got to try and find the mass of the airplane. So I'm going to go back. Now I can go back to this equation, and I know I've got the acceleration, I've got the force, I just need to find the mass. So again, I'm going to use our little FIFA method, and you can do this for the first equation if you need to as well, to make sure I'm rearranging correctly. So F equals m times a, force equals mass times acceleration. The force we know up here is 750,000. Mass I don't know, so I can leave it as an x or an m. Acceleration I do know, and that gets you marked here, even if you mess up from there. But to get rid of a times by 2.5, we are going to need to divide by 2.5. So on this side of the equation, divide by 2.5 equals m, and you stick that in your calculator. Therefore, m equals 300,000, which seems very high, but don't forget, we're talking about an airplane, so it kind of makes sense. Okay, next question we're going to look at is another motion one, because these can be the trickiest, because there's a lot of things that could be thrown at you, and a lot of equations to use. Now, for context in this question, I've kind of just given you the actual numerical bit. There's a car that travels at a constant speed between 2 speed cameras, then it decelerates and stops. So that's going to help us answer this first bit. Okay, so it says the camera recorded 2 images, don't forget, going at a constant speed, and they are 0.70 seconds apart. It travels 14 meters between those images. Then it decelerates, and the maximum deceleration of the car is 6.25 meters per second squared. It says calculate the minimum braking distance for the car at the speed it passes the speed camera. Now, multi-step, this is a big one. It's got 6 marks and there's no units. That shows us there's quite a lot to do here. Okay, quite a lot to figure out. So first job then is, before we do the minimum braking distance, okay, let's just write down every equation we can that might be helpful. So we got the obvious distance equals speed times time. We can write down acceleration, because I've got deceleration there, that might be useful. I could write down the big, long, confusing v squared u squared equals 2as, which I'm making a meal of here. You could write down any other motion equation really that you wanted to. but it should be obvious that some are more helpful than others, okay, because we've got time, we've got speeds, we've got decelerations, we've got distance, okay, so these have all got a combination of those, so actually it's just those three we're going to be looking at so far. So let's start to label these up then. Now, minimum braking distance, we're going to use S. Deceleration is basically this negative acceleration. It's acceleration, but it's negative, meaning it slows down rather than speeds up the car. And we've got a distance here again, and we've got a time. Okay. Now, to work out a distance for it decelerating, we can't use this straight away because that implies it's going at constant speed, which we know it's not, because it's decelerating. So what we're going to do then, and let's look back at the bit of brackets here about earlier in the question, the car travels at a constant speed between two speed cameras, then decelerates and stops. So I've got a distance, I've got a time, so I can work out a speed there kind of relatively simply. Now, to be able to do that, we need to plug in our values. So using FIFA again, I've got distance is 14, speed I don't know, time is 0.7, so therefore the speed it's going at that point there is going to be 20 meters per second. Okay, so that again is a couple of marks just for working something out, even if you haven't got close to the final answer yet. However, this helps us because that is a velocity and that is an initial velocity. Okay, even though I've written v there, that's an initial velocity because that's what it's going before it starts to decelerate. So I'm going to, from here on in, term that as u instead of v. Then we've now got a velocity and it says it decelerates, and essentially it decelerates and stops. So even though it's not mentioned in the question, what that tells us is a final velocity is going to be equal to 0. Okay, so its initial velocity, it's going at 20 meters per second, then it's going to be going final velocity, it's not moving, it's stopped. So final velocity v is equal to 0. So now if we look at it like this, we've now got an initial and final velocity or final speed. We've also got an acceleration, even though it's negative because it's deceleration, but that doesn't matter too much here. And actually, this little thing here, S, stands for distance. So we can actually work out the distance by using this equation here. So let's write down our equation and see what we can do with it. I'm going to use FIFA for this bit, definitely for this equation, because it is really easy to go wrong. So our equation is v squared minus u squared equals 2 times a times s. Let's plug in our values. Our initial speed, we said it's going at 20. Final speed is 0. I'm going to put it in to show that to an examiner I know what I'm talking about, even if, you know, I know 0 squared is obviously 0. And on this side, the acceleration is, don't forget the deceleration. It could be negative here, you could do a negative, it doesn't really matter because the distance is just the distance. And that's going to be times by s. Now actually here, instead of writing s, because my 5s look like s's, I'm going to write an x just to show you can use x there if you wanted to. Okay, so let's then simplify this out a little bit to make our lives a bit easier. That means 200 squared is 400, minus 0 is obviously 0, is obviously still 400. I'm going to do these two initially just to make lives a little bit easier. 2 times 6.25 is 12.5 times x, just to make it easy to figure out what to do because it's hard to rearrange this equation. So now I've got 400 equals 12.5 times by x. So to get x, I need to get rid of the times by 12.5, which is 400 divided by 12.5. And if you stick down your calculator, you should get that to be 32 meters, which is a whopping 6 marks. So it's actually 4 for this bit here, because it's quite a tricky equation with a rearrangement included. Right, next question, going strong. This one is another one that has magnetic flux density in it, so let's have a look what we've got. So magnetic flux density, it tells us a length of a copper rod, tells us a mass, tells us a current, and tells us a teacher closed the switch and a copper rod accelerated from rest for 0.15 seconds. And it asks us to calculate the maximum possible velocity of a copper rod. This is a really tricky question because it's the kind of question where actually you probably haven't seen anything quite like this before in terms of what the equation is asking you to do. Like we said before though, a couple of questions ago, there's only one equation that has flux density in it. So let's just write that one down straight away. So we got rid of, so we've got B, flux density, we've got length, we've got current. So what we're left with is we've got time, we've got mass, in grams, and we've got velocity. So let's have a look at what equation we could use that have got mass, time, and velocity in. It should be obvious there's only really one we could use, which is force equals mass times by velocity, or change in velocity technically, divided by time. And they both have force in, okay? So once you've done enough of these, you'll start noticing that both equations will have something similar in to enable you to work out the final answer. So let's get to work then using this equation to work out the force. So force equals flux density, which is 0.3, times by current, which is 1.7, times by the length, which is 0.05. So if you plug all those values in, you should get, again, it's quite a small force because we're talking about a wire experiencing a force due to a magnetic field, happens to be 0.0255 newtons. So that's a couple of marks already sorted. Next then, let's figure out what we can do by substituting into this equation here. So again, I'm going to use our friend FIFA to make sure I'm rearranging it correctly. So F equals mv over t. The force I've just said is 0.0255. Now the mass is in grams, that needs to be in kilograms. You want to write that down straight away just to make sure the examiner knows you've got it somewhere. So that equals 4.0 grams equals 0.004, so divide by 1,000 kilograms. So let's write that down properly down here, so 0.004. Now the velocity I don't know, that's what I'm trying to find, so I'm going to leave it as a v, or we can leave it as an x for now. And then t, time, is up the top, 0.15 seconds. So let's then figure out how we can get our final answer. So what I'm going to do is a couple of stages at a time just to make it a little bit easier. Let's get rid of my 0.15 first, so 0.0255 here. That then changes to this side. My top of fraction stays the same. But we can then say, okay, to get rid of the times by 0.004, I can then divide by it. Okay, so you do this in all one swoop just because I've not got much room here. So get rid of it from this side here. If you make sure you keep an eye on the brackets and you make sure to divide correctly by what you need to do, then what we can do is figure out our total velocity should be 0.956, which is not really a way of checking if that's correct or not because you don't know the context of the copper rod, but it's not faster than the speed of light and it's not insanely slow, so it sounds about right to me. All right, I hope you guys are ready for the hardest ones of the whole of paper 2. Okay, these two questions here, I reckon, are two of the hardest kind of multi-step equations you could be asked about. Now, this one's particularly hard because it talks about springs. It also involves an equation which you normally see a bit on paper 1, but it could come up in paper 2 as well. So let's see what we can work out. So it says, student has a weight on a Newton meter. The energy stored in the spring, it tells us, is 4.5 times 10 to the power minus 2. If the student increases the weight by 2 newtons, then it says calculate the total extension, and it tells us the spring constant. So I'm going to write down my symbols here: K for spring constant, E for extension, and force for newtons. Now this one is weird because it says 6 marks, but it kind of doesn't seem like it's giving you that much. It's giving you 3 things and asks you to work out a 4th. However, your clue is that actually to find the extension, there's no way you can find the total extension without actually finding what the extension is initially. Okay, so we've got a force here, and we could just try and work out, oh, what do? I work out the total extension, put them into an equation. However, it doesn't initially, because it says there's a weight on the Newton meter, the energy is stored is this, then the person increases. There's like 2 sections to this question, basically. Okay, so what we're going to do first of all is to find the initial extension, so when the weight is on it initially. Okay, so to be able to do that, and always write down what you're doing so the examiner knows what you're talking about, I'm going to do this equation here. So the energy, elastic potential energy, is half times by K, spring constant, times by extension squared. Now all these values I have other than extension, so I can just plug those in and see what we find out. So doing FIFA all the way to make sure we rearrange correctly, 4.5 times 10 to the minus 2 equals a half times by spring constant, so that's 400, times by our extension squared, which we don't know yet. So let's make life simpler. And when we're doing our fine tuning, half times 400 is 200. Just to make it easy to figure out what to do next with that. And then to get rid of a times 200, we've got to divide by 200 to find out what our extension squared is. So 4.5 times 10 to the minus 2, divide by 200 equals E. Now, because it's E squared, in that case, we've got to then, to get rid of a square, we've got to square root both sides. So square root E squared basically becomes E. Square root the same to the other side, otherwise it doesn't work. So you can do this sum first, then put in your calculator. It doesn't really matter. Anyway, if you do that all together, you should get the initial extension is 0.15 meters. Okay, now what we've got to do is then say, well, that was the extension initially. I've then got to find the new extension, okay? Because it says calculate the total extension. So the spring has already extended by a bit, and now it's going to extend by a little bit more once I put more weight on. So it's going to get even longer. So find the new extension, we're going to use the force because we haven't used that yet. I've also written N there instead of F for force, M for newtons. So the new equation we're going to use is force equals spring constant times an extension. Okay, so the new force is 2.0. The spring constant is the same because that's a property of the spring. and the new extension, I don't know what it is. So I'm just going to go to this side over here just to make it a little bit more straightforward. To fine tune it, my extension is going to be 2.0 divided by 400, which equals, and we're in meters here, that's going to equal 0.005 meters. Okay. To then work out the total, this is why this is a really, really hard question. I'm getting my coloured pen out just because it's so hard. That's 0.005 meters. Up here we've got 0.015 meters. We've got to add those two things together. So to find the total, that then means 0.015, so how much it was stretched by initially, then how much if we add the extra mass on. And that then comes to 0.020, which is about 20 centimeters, which doesn't sound too ridiculous for a spring. So well done, guys. Got there in the end. If you don't think you can cope with a question like that in an exam, like I said, just work out something first. It will help you later on. And to finish off, we've got another one of, in my opinion, the hardest ones on the paper 2 you could get, which is combining moments and a magnetic force or magnetic flux density. Okay, so let's have a look at what we've got. We've got a situation here where we've got a small weight placed on a bar with wire X, makes it balance its original position. It says it's 8 centimeters away from a metal support. There's a weight, there's an insulating bar, and there's the wire there. The wire's kind of coming out from the page, if that makes sense. Okay, so the wire is 5 centimeters long, so that's L, has a current of that, and there's a clockwise moment, which we haven't come across in these questions yet, which is 4.8 times 10 to the minus 4. The equation asks us to calculate the magnetic flux density. So let's have a look at what equations we could use. Now, luckily for us, why this is a hard question to understand, the equations, there's only two it could possibly be. There's only one equation that has moment in it, and that's moment equals force times distance. And the other equation is the one to do with magnetic flux density. So magnetic flux density we've come across a couple of times already in these questions. F equals flux density times current I times L. Okay, now we're trying to find flux density, so let's have a look at what we've got so far. Now we've got current and we've got length. We don't actually have force, so we can't do this yet because we don't have what force is. However, now we know what the moment is. We can, if we keep our wits about us, we say we've got a moment and we've got a distance. We've actually got two distances, which I'll come on to in a second. Then we can find the force that way. So I'm going to do that bit first. So I'm going to say moment equals force times distance. Now the moment is the easy bit, 4.8 times 10 to the minus 4 Newton meters. Force I don't know. Let's have a look at what distance we're going to use, because there's a couple of things here we get confused by. Now the length of the wire is, well, there's two distances, right? I've got 8 centimeters here. It says the wire is 5 centimeters long. You've got to be really careful because it says the wire is 5 centimeters long. So that means that is this L here. That's how long the wire is. However, it says it's 8 centimeters away from the pivot. Now, if you remember this equation correctly, it's not actually distance, it's distance from a force or line of action of force to a pivot. So it's this one we're going to use here, and it's in centimeters, so making it extra hard to use. 8 centimeters divided by 100 equals 0.08 meters. Okay, so let's find the force then by just kind of working now initially. So it's 4.8 times 10 to the minus 4 divided by 0.08, and that then gives us a force of quite a small one, 0.06 newtons. Okay, but now we know what that is, and that's 3 marks automatically. We can then put this back into this equation to work it out. Okay, so I'm just going to go down below a little bit, just so we've got plenty of room to be able to use it. So magnetic flux density, so F equals B times I times L. So the force we just worked out, 0.006. Flux density, I don't know. Current, I do. Current is 1.5. And length, as we said earlier, it's 5 centimeters, so 0.05 meters. Okay, so then finishing off, we've got 0.006 divided by 1.5 times 0.05. Leave it in brackets to make sure you're getting all your marks, so you're not messing up a rearrangement. And you put that into your calculator. That then comes to be 0.05 overall. Okay, there is a mark here for units. So the unit is the T, or the Tesla, for magnetic flux density, as we've kind of seen previously in some of these answers. So there we go, we got there, made it in the end. That's some multi-steps, probably the hardest ones you could get on paper 2. So prepare for the hardest thing, and then you won't be surprised if it comes up and you won't panic and you'll be able to answer them.